Brought some old-fashioned visual aids. This is not 3 copies of the same book. This occupies 11.5 inches on my shelves. It weighs 15 pounds, and it's a collation of 5 manuscripts of the Rus Primary Chronicle, which is an old Russian historical text. It began to be composed probably in the 10th century and was edited several times before it reached a more or less finished stage at the beginning of the 12th century. The earliest manuscripts we have are from 1377, so the manuscript evidence for this text is later than the finalizing of the text by at least a couple of hundred years. Most of the manuscripts are later than that. The brown volume that is about to make its way around is a facsimile of one of the manuscripts. It's the only one that has pretty pictures in it. And this text is important, indeed more important than anything else, for the early history of Russia and Ukraine, and for that reason the Harvard Ukrainian Research Institute decided it might be useful to study it. And the problem with studying this text is that it exists in several manuscripts, all of which are different, because in the course of copying manuscripts you make changes, sometimes deliberately, sometimes inadvertently. So your first task when you want to study the primary chronicle is to figure out what it is. And the way we do that is we take the manuscript evidence and we collate and align it. That is to say, we take the corresponding passages from different manuscripts, we compare them, and we evaluate the variation. And the methodology for evaluating the variation is fairly complex. It's not simply a matter of taking a vote and using the majority one, and it's not a matter of taking the oldest reading. There are strategies for evaluating the quality of the readings and deciding which ones you should prefer where they differ. The idea for this paper edition was born in the 70s, and I worked on it in the 80s when I was a graduate student. The general editor is a historian, and historians famously aren't particularly good at reading manuscripts. The people who are good at reading manuscripts are historical linguists. So I was a graduate student in Slavic historical linguistics at the time that Don was editing this, and he hired me to do the manuscript transcriptions. So I sat there with books like that and microfilms and the like, and I turned it into a character transcription. And because if you ever worked with manuscript materials, there are many instances where you can't really tell what you're looking at. There's no division between words in most of the manuscripts. In some cases, you can figure that out even intuitively, and in other cases, there are genuine ambiguities and you have to make a decision. There are letters that could be this or could be that, and you have to figure out what the shapes represented in the context. So although they started this in the 70s and I worked on it in the 80s, the print edition saw light only in 2003. And as soon as the print edition came out, we said, well, it would be kind of nice if we had an electronic edition so that people didn't have to lug those big books around. We had done the typesetting for the print edition in an ancient typesetting system called TROF. It was designed primarily for formatting documentation on the Unix operating system. And that was the technology we had at the time. We did the work on a mainframe, we designed our own fonts, and we typed all of these stupid little formatting codes into the files so that we could produce the books that you see in front of you. But because that was a formalized structure, we were then able to repurpose it. So as soon as the print edition hit the shelves, I converted the TROF code into XML and then began to do other things with it. For the print edition, we would have liked to have everything aligned by word, because that's the level at which you typically do the comparisons, but we didn't have the wherewithal to do that. The alignment that we have in the editions you were looking at is by lines. So this is the first line of the text as it appears in 5 manuscripts, 3 printed editions, and this is our reconstruction. And you can see, even if you can't read Cyrillic, you can see at a glance that they differ. And if you can kind of read Cyrillic, which you can do because, hey, half of the letters are the same as in English, you can see at least that there is, for example, a word at the beginning of these two that is not the beginning of those. So the first word here corresponds to the second word there. So to get all of that aligned properly in the print edition was beyond our abilities when we were doing Stone Age typesetting. but it was something we always wanted to do. Because we had an aligned by line in that edition, I was able to create something like this very easily. And I've had some version of this online for quite a while. But what I had in the back of my mind was that I would always like to have it aligned by words. There is, in fact, a piece of software that purports to do this. It's called CollateX. It was developed at a research institute in The Hague. It's open source. You can fork it and play with it. And it takes manuscript witnesses, that is to say transcriptions of the different manuscripts, and it tries to align them word by word. This is a computationally complex problem. If you think about how you would align two manuscripts the naive human way, you take one of them and you string it out, and then you take the other one, you take the first word and you read across and see where it matches. And then when it matches, you take the second word and see whether that matches too. And these are long texts and they have repetition. And now imagine that you're aligning 10 different witnesses and you run into exponential computational complexity, which is to say you can't do it. So there are all sorts of strategies, heuristics for working around this that may not get you an optimal solution, but they do get you a solution before the sun burns out. And that was the problem that CollateX was designed to solve. CollateX, however, is designed to work primarily with normalized texts. So the texts on which it excels are texts where everything is spelled pretty much the same way. So if you have variation, then the variation is significant. And in our case, some of the variation is significant and some of it isn't. And it's not the difference between significant and insignificant variation isn't something that we can describe in a very generalized way. We could say, for example, that whether a letter is superscript or inline doesn't make a difference. That's kind of obvious. But there are certain letter substitutions that matter, certain ones that don't, and most annoyingly, some that matter in some positions but not in others. So when we took these texts and ran them through CollateX, we got a mess. It wasn't really able to align it very well because everything differed from everything else. So the task that we set ourselves was to build a preprocessor that, based on our knowledge of Church Slavonic orthography, would level the variation that isn't important for collation and alignment purposes, but retain the variation that is. And we could then take that normalized version, feed it to CollateX. It would align the words correctly. We would keep a pointer from that simplified form back to the original orthographic form, so when we generated output, we would get our output in the original orthography. So this is the new improved version. We have our reconstruction on the top, and this is the entire one, so you can kind of scroll through it. The line numbering is conventional in the study of early Russian and Ukrainian history, so that's a reference system that everybody understands. And the idea is that you might read through this, and when you find a moment that you're interested in, you click on the line, and the part down below is going to give you the collation for that line. And as you can see here, there's a word in, say, here that isn't in there. So there are a couple of places where there's going to be differences, words that are included in some but not in others. The pre-processing that we do normalizes the text in ways that we'll talk about a bit later. Some of it we won't talk about because it requires a knowledge of Church Slavonic orthography and the details won't be interesting, but there are some general principles involved. And there are also places where it misfires, and the places where it misfires are then those where we're going to have to go back and think about a post-processing stage. So the workflow we have now, and Minas will talk more about this later, is we take what are called diplomatic transcriptions, the very literal character-by-character transcription with the letter forms that occur in the manuscripts. We create a shadow normalized copy that CollateX uses for the collation. It gives it back to us, and then in places where it misfires, we're going to have to go in and fix it. The normalization that we used is based on a 100-year-old technology called SoundX, which some of you may have run into. The SoundX was developed in the teens to solve a filing problem, and it wasn't computational files, it was manila files with names written on tabs. And the problem was that there are people who have more or less the same surname, but spell it differently. So I have the same surname as the Israeli musician Daniel Barenboim, but if you try to look him up under my spelling, you won't find him, and vice versa. So the idea behind SoundX, which was designed specifically to deal with English language surnames, was that it would retain the parts of the name that are meaningful, get rid of the parts that aren't, and it's essentially a hashing algorithm. And then my name and Daniel Barenboim Birnbaum's name would hash to the same value. And if you're looking up somebody and you know the name but you're not sure of the spelling, because names have variant spellings, you would look it up by the hash. There have been several variations on SoundX since it was developed. It was developed specifically for, not just for English, but for English surnames. And one of the things that quickly emerged was that it doesn't do very well with Eastern European surnames because, for example, W's and V's are often interchanged and the sound ch can be spelled in different ways depending on the Eastern European language you're coming from. So there is a version of SoundX that was developed by a Jewish genealogical society specifically to deal with Eastern European immigrant surnames. So we figured, why shouldn't we have one for medieval Slavic writing? So the starting point was to look at the orthography that occurs in the manuscripts, figure out which parts are significant, and develop what's essentially a hash that will let us do the alignment. One of the other things that helps us in this project is that we had already done a course alignment by line. So if we had to take the entire manuscript, there are over 8,000 lines. If we had to take lines of this sort, if we had to take the entire work with all of the manuscript copies and treat them as one big line and try to align them, there would be more misfires because there are just places where the algorithm, which is after all a heuristic, isn't going to get us where we want to go. So to leverage the fact that we already had them divided in lines, we treated this as 8,200 separate collation problems. So we broke up the document, we fed each piece to collatex, we got the results back, and then we zipped it up together. I'm at this point going to turn the floor over to Minas, and he's going to talk about the workflow and the different parts that led us from those fat books to what you see in front of you. Do you want to drive, or shall I do that?
We can drive. First of all, speaking of errors, you can actually see an error right here. There is a foot here that should have been here, but pretty not there because there's nothing here or here. So, you know, that's just probably one of the more common errors that we see all the time, unfortunately. And we are thinking of different ways to deal with that later on, but right now we don't really have much of a say. Can you go to the manual page? Yeah. So if you go here and you want to follow along, that would be fine. But this outlines the basic process that we went through. So what does this actually mean? So in the lower line here, we have file formats that, you know, the data goes through different transformations. The upper levels are what does the transformation. So we start with some form of XML file. If it is not in TI format, which you can ask David about this because it's complicated, it's basically a standardized form for different versions of texts in a very simple form.
So this is not TEI.
Yes. So if it is something like this, then we run it through an XSLT that transforms it to a TEI, and there should be a version of this somewhere, I think.
So this is the TEI version of that same thing. The textual content is the same, the markup is changed. The TEI is the Text Encoding Initiative. It's a set of guidelines. They like not to call it a standard. It's a set of guidelines for encoding texts in the humanities in XML. And the point of providing guidelines is that it would make it easier for people to develop interoperable tools and, for that matter, interoperable texts.
Can we go back a little bit? So if your text is not in TEI, we do this to get into TEI, and even if it is, it still needs to go through at least one more transformation, which is tokenization, which is also done by XSLT. So what that does is it basically wraps a W for word element around every single word, and the process by which that's done, it's a little more complicated. Well, it's a lot more complicated than simple tagging around white space, because sometimes you have different things like punctuation, sometimes you have different numbers in there, sometimes you have markup in there that you want to present to preserve, and the markup itself can have white space as well. So, you know, it's more complicated than that, but ideally what it produces is actual W elements around every single word, which is basically what you see here. So we end up with something like this. And once we have that, we go on to transform that information yet again to be able to be taken as input to collatex. Because while collatex is a very powerful tool and it helps us a lot, like if it didn't exist, we would not be able to do this project pretty much, at least not in this time. It is pretty picky when it comes to its input, but thankfully one of the inputs it could take was JSON files. So what this Python script does, which I can show you later, or you could see the code yourself on GitHub, there's a link somewhere here, is it converts this into a version of something like this. So what is this? Here you see the T, which is what the original token looked like, which David talked about before. N is the normalized form, so that is whatever is the output of the normalization algorithm, the soundtext. So when Colitex looks at things, it entirely ignores the T, and it only looks at the ends, and it compares the ends. And when we look at this data later, you will see how it's very beneficial, because if you look at different versions of the same word, if you look at their normalized representations, most of the time they are pretty much identical, with occasional error of by 1 or 2 characters, which is, even that is very, very rare. So this definitely proved to be a very robust algorithm, and I will go into detail as to how it actually happened eventually. And the U value is what you saw earlier, were the numbers before the lines, which is basically the page number and the line number. Yeah, those things. So it says first page, first line, basically. Okay, so once we had that, we were finally able to call Colitex, and yeah, and this would be what its output is. Colitex is actually a Java application, so there was a bit of a conundrum, because, well, we tried to limit ourselves to only Python XSLT, because, well, the two of us know it reasonably well, but neither of us is any good at Java, so we really tried not to use it, you know, if we could help it. Thankfully, I found a way to actually call and spawn a Java process using Python, which you can see in the code if you want. But it's actually very nifty. You are literally sending command line command, and it spawns it as if it were an actual Windows command. So you can call pretty much anything you could run from command line using a Python script, which is very nifty. And what actually that helped us do, if you want to scroll up a little bit again, that allowed us to have a wrapper that actually took us from here on all the way down here without us having to run 1, 2, 3 different Python scripts. Instead, you just run one single wrapper, and it just goes through this pipeline by itself, and it produces wonderful output. So this is what this signifies, that Java is a Colitex application, so it is not actually being called directly, but it's called by a Python script. And the output of Colitex is yet again a JSON file, and if you go to that, you will see that it's aligned much better. That's not it.
Yes, that's
Yeah.
the Colitex
Okay.
output.
Okay, so here you see you pretty much can't really tell the difference by just looking at this compared to what was before, but it's definitely a different structure, and it is structure that Colitex can understand. And for example, here you can look at the same word as it appeared in different manuscripts. So for example, here you can see the differences in the T values, but the ends are staying the same. And this is what I was talking about, that there could be spacing and there could be different elements inside the W, but regardless, we're able to parse it. And once that is done, we yet again call a different Python script that takes this and converts it into XML, which is much more readable. So again, you can see here there are differences. For example, here is a Latin-looking I, whereas here it's an E. There's different capitalization. There is punctuation difference. There's a period there and a comma there. There is a random line break element there in the middle of the word. So, you know, there are a bunch of differences, but through going through this wonderful pipeline, we were able to collect them regardless on the word level for most of the words. And the final step would be, after this is generated, it goes through yet another XSLT transformation, which takes a bunch of little XML files that we just generated, and it creates one HTML page, which is what David was showing before, which is in essence a reader where you can compare different lines all at once, which is what we're looking at from the very beginning. So here are the different scripts. I believe there are a total of 6. Yeah, there are 6 scripts. We ended up not using this script because it's in essence synonymous to this one. It just took a different version of input. But here's what's happening. This is the first script. This is the one that, as you can tell from the name, it takes the XML, which is in TEI format, and it transforms it to JSON. And as I said, all the code is available on GitHub if you want to take a look at it, and I can read through it if you want to. Run Colitex is the one that calls Colitex from Python, so Java application. JSON to XML is the one that takes the output of the Colitex and creates the XML version afterwards. Preprocessing has all of the functions that are called by different scripts. Mainly, it is the normalization algorithm, which I tried to make it as functional as possible because that was just a lot easier to edit if everything was broken down as opposed to having one giant code and go figure what's happening there. So I think it's fairly readable. There's a function for stripping punctuation. There is one for normalizing Cyrillic numbers, which are just a hell. Yeah, it's apparently Cyrillic system, and David can comment more on that. They use very different numbers from what we're used to. It's very different from what the Roman system is, and it's different from what Arabic is. It's a bit of a blend of the two, but not really, so it had to require its own set of rules to normalize it. Well, actually, we normalized Arabic to Cyrillic, not the other way around, so that was not easy either. Anyway, so it has a bunch of functions that do the preprocessing and normalization, and wrapper, as I said, is the script that calls 1, 2, 3 in order. So here's the normalization algorithm. And you can basically read through it and understand what's happening, but to give you a brief overview, what happens is that, as I said, first of all, some of the words come with internal markup, and while we want to keep that in the our tier representation, when we go to the normalized text, we want only text, so we don't want any markup, anything else. So we get rid of, we keep the contents of these elements, but we get rid of the elements themselves, if you will, the element tags, if you could call that. We get rid of all of these elements because they are actually empty elements for the most part. Del is different because it means something was deleted. But PB or LB, which is page break and light break, they are empty elements, so deleting them doesn't really affect anything, but you get rid of it. Choice was a bit of a struggle because choice has nesting. So, for example, if you have something like the word example, and when you would get to the letter A, you have a choice element, and then you would have orig, which is original O, and reg, which is A. So that means that and then the choice element closes and the word example continues. That means that example could have been spelled either with an O or with an A, and you need to make a judgment to choose one of those. So for these, we just organized them in pairs. So given these, we took the correction, we took the regular spelling, and we took the expanded if there was an abbreviation. And sometimes it was just a segment, which it didn't really matter as to which one we chose, so we just chose the second one by default. So that was just an extra challenge, and yet again, that was solved in the preprocessing script. And as far as all other markup, which there really should not have been any more at this point because we followed TI guidelines, but just in case there was any, we stripped it, just to be safe. And at this point, we went on to remove all the punctuation, and if at this point, once you remove the punctuation, the length of the token was 0, that means that there was only punctuation there. And this actually used to throw the algorithm off for quite a while at first, because we didn't understand what was happening. And what happened was that there were basically empty elements there, but they came because at some point there was punctuation there, and then it got removed, and well, there was nothing there to compare to. So that was fixed. And then we processed the numbers, and at this point we're only stuck with Slavic Cyrillic characters. And at this point we go on to apply multiple rules, which you can see in this soundx rules file. Might be helpful if you want it. Which is basically normalization of the orthography, which David compiled. Yeah. So it applies different things. There are 3 sets of rules. There is many to one, where multiple letters map to a single letter. There are rules where it's one to many, where one letter maps to multiple letters. And then there is one to one, where any one of these letters maps to this thing. So it's not like this sequence maps to this, it's every single one of these letters maps to this. Yeah. If you look for that sequence, you would never find it. And I guess that's counted by difference in just stripes writing, right?
And these These have to be applied in order for feeding and bleeding reasons.
Right, otherwise they would interact and you would get things that you are not expecting at all. So this has to be controlled pretty well. And they are applied in this order. Can we go back to the manual? Yeah. So once that's done, we handle what we call the special vowels, which the knowledge of the people who know Russian would know as the mягкий знак and tвердый знак. Yes. Because in ancient Slavonic, and again David can talk to this a lot better than I can, they used to be actual vowels, but they couldn't be centers of syllables. Is that right?
The common Slavic had short high vowels that over the course of the development of all of the Slavic languages changed according to their position, and in certain positions they became other vowels, and in other positions they disappeared. And that's significant because our manuscripts date from a time that kind of surrounds their disappearance. So they're often present in the orthography without having linguistic significance, which means if we have two consonants divided by one of those and the vowel wasn't pronounced, we're going to treat that as a geminate consonant and degeminate it. If we have two consonants separated by a different vowel, though, we're going to keep them. And then at some point later, we're going to strip all of the vowels except the ones in initial position, which has to do with the extent to which vowel letters do and do not carry meaning in early Cyrillic writing, where initial vowels are more meaningful than later vowels. So we have to strip the vowels in two places. We strip the so-called years, the short high vowels first, then we degeminate, and then later we'll strip other vowels.
So the next steps is what David just went over. So NN is probably the most common combination of same consonants, so geminate consonants in Russian and in also Slavonic. So we had to degeminate that to become a single N. And this was a little tricky to do code-wise, but it was doable eventually. And at this point, most of the words actually ended up being very short, so 2 or 3 symbols, but we wanted to account for length because we wanted to make sure that we're comparing things of the same length. So we normalized everything to be 4 characters long. So what happened is that if the normalized form was, for example, 5 or 6 characters, we just cut it off at number 4. Because frankly, most of the common things in a word happen, at least in Slavic language, they happen toward the beginning. So you're more likely to have more variation toward the end, so we cut it off. And if the word was shorter than 4 characters, then we just padded it with X characters, which would always map to each other. So it was just a placeholder for, there could be a character here.
And that's something that we adopted from the original SoundX algorithm, where it turns out apparently in English language surnames, the beginning of the word is more meaning bearing than the end of the word. The normalization we're doing here is to support collation and alignment, and that's separate from evaluation. So there are, for example, in the history of the Slavic languages, there are multiple simple past tense forms, aorists and imperfects, which differ in their endings but not in their beginnings. And whether one manuscript has an aorist and another one has an imperfect could have textological significance. So in terms of evaluating the variation and deciding where it's meaningful, we do want to keep that. But in terms of aligning the words so that we know that we want to compare these 2 words and not other words in the sentences, we don't. So the normalization that we undertake for collation and alignment purposes is going to be different from the normalization we will undertake for evaluation purposes. But for the evaluation, you have to come back next year.
This basically concludes it because, well, that's what we did. And if you are on this page, you can follow here the link to GitHub, and if you go through the scripts directory and under there, you can see all the code if you're interested to read that. I guess the most interesting would be the preprocessing because it has all the functions. Yeah. So I'm not going to go over every single thing in here, but the function names are fairly descriptive as to what do they do.
And what does remove element tags do?
I don't know. So a lot of this, there were multiple ways to approach something. For example, again, for remove element tags, what you could do is you could do some smart string parsing and find if you're inside the element and get rid of that. But that's a little risky because first of all you could have nested elements and it could break there multiple levels, and you could just have different things that you're not expecting because it's a string. So instead I tried to use the XML library Minidome, which is my favorite by far, to do all of that. So for example, for remove elements, I'm not actually doing anything as far as string parsing. What I'm doing is that I'm taking the child of the element, which is the text node, given how XML is structured, and I'm replacing the entire element with its child's contents. So it's in essence removing the element tags, but in actuality what it does to the structure is it actually physically changes, I guess, the grandchild for the child position for the element.
This is basically JavaScript rewritten as Python.
Pretty much. One more thing I wanted to mention is the choice of languages, as in why was this Python and XSLT and not anything else? Well, aside from the obvious choice that David is good at XSLT and I'm good at Python, was the answer was that you could potentially do everything in Python for this project, but you could not do everything in XSLT. The reason we chose XSLT is, well, one of the reasons is that it's obviously a native language for working with XML. It's that is already in XML. It makes sense to use it for transformations, etc. And on some levels, it is actually more robust than using Python because at some point we did duplicate tasks. We did the same task, each of us did, and for one reason or another, David's was more optimized, mainly because it is XSLT as opposed to Python. But another thing is that XSLT has absolutely no way of spawning other processes from command line, so we definitely needed some form of a general purpose language, and Python obviously worked. But yeah, theoretically, this entire project could have been done in Python alone.
The starting point for looking at it in Python, because our input is XML and our output is XML, so it would have been nice to keep it that way all the way through. Once we had to manipulate JSON, then it became sensible. You can read and write JSON in XSLT. Writing it is easy, reading it is not. The XSLT 3.0, which is currently under development, does have native XML to JSON and JSON to XML functions, but the fact that it's currently under development means that it's a moving target, and the XSLT processor that we use is written by the guy who edits the XSLT spec, and his processor isn't in sync with the current edit stage of the spec, so we didn't think that that was going to be a safe solution for a project at this point. The parsing, so in any case, one of the other things that led us toward Python was that there's a lot of string manipulation here, and XSLT has good string handling facilities. It has regular expression support, but Python manages many of those functions more elegantly than XSLT. On the other hand, parsing XML markup using regular expressions, using string handling, is perilous because there's a lot of variation that's permitted in markup that isn't informational. And if you're parsing using something like regular expressions, you have to account for all of that variation. And which is why it makes sense, if you are going to be handling the XML at any point in Python, to use a library that simplifies all of that for you.
Can you remind us why you needed the JSON formats?
CollateX reads and writes a variety of formats, including TEI XML, but there are two reasons why that wasn't satisfactory for us. The first is that the TEI XML output isn't as rich as the output that we needed. We're out, for example, when we get our output from CollateX, there are going to be some misalignments, and if we've retained our SoundX normalizations as attributes on the words, we can access those later and in post-processing clean up the misalignments. If we let CollateX generate TEI output, it throws that away because that's not part of the TEI standard. CollateX has richest support on both input and output for JSON, so if you use any of their other input and output formats, you lose something. And for that reason, we decided to talk to it in its own language. I'm curious about that decision because JSON, of course, is lighter weight than XML, but this isn't a transport language. This is a markup language, and you can read the XML. You can't really read the JSON. So I'm not sure why they decided to privilege JSON. They do have a web service, and it may have been because they wanted to speed the transmission of the information, which makes a certain amount of sense, although typically you have to get it out of JSON on the other end anyway.
Questions? I guess we should.